What does it take to build a blade so massive that it can sweep an entire football field in one rotation? And yet, it must be light enough to float in the wind? As the layers build up, the factory comes alive with activity. Teams of specialists move with practiced precision, unrolling vast sheets of fiberglass, trimming edges, and smoothing out every wrinkle. Each section of fabric is meticulously mapped according to computer models, ensuring the fibers run in exactly the right orientation to handle the immense forces the finished blade will face. It's not just about strength, it's about aerodynamics too. The slightest deviation could create turbulence, robbing the turbine of precious efficiency. Once the layup is complete, it's time for the infusion, a pivotal moment where chemistry takes center stage. Miles of tubing are carefully snaked across the mold, and powerful pumps draw a vacuum, sucking every last molecule of air out of the fiberglass layers. Then, with the hiss and gurgle of pressurized lines, liquid resin is injected. The resin seeps through the fabric, saturating every fiber and every pore of the balsa wood. This is a race against time. The resin begins to cure as soon as it leaves the tank. If it sets too soon, the blade will be riddled with weak spots. If it flows too slowly, the process must start again from scratch. As the resin hardens, the factory's ovens, some as long as a city block, are fired up. The entire mold is rolled inside, and the blade is baked at precise temperatures for hours. This curing process is what transforms the floppy, fabric and wood assembly into a single, seamless shell of composite material. Sensors embedded throughout the blade monitor temperature and pressure, feeding data to engineers in real time. Here there's no room for error. The wrong temperature could warp the blade, rendering it useless. Once cooled, the blade is carefully pried from its mold, a tense operation requiring cranes, hydraulic lifts, and a team of experts. The blade's skin must be flawless, free of even the tiniest crack or bubble. Technicians tap along the surface with mallets, listening for the telltale sound of a void. Ultrasound scanners sweep across the blade, searching for internal flaws invisible to the naked eye. Only blades that pass this battery of tests advance to the next stage. But the raw blade is only half the battle. Now comes the finishing work, where brute strength gives way to delicate artistry. Massive sanders and grinders shape the leading and trailing edges, sculpting them into aerodynamic perfection. Workers in protective suits apply layers of primer and paint, not just for aesthetics but for protection against the relentless assault of sun, rain, and ice. Even the color is carefully chosen. The pale hues help reflect sunlight, keeping the blade cool and reducing thermal stress. Next, the blade's root, the end that will connect to the turbine's central hub, must be reinforced. Engineers fit it with steel bushings and anchor points, designed to withstand forces of hundreds of tons. Every connection is torqued to exacting specifications. Each bolt and fastener will eventually be all that stands between the spinning blade and disaster. Before it ever leaves the factory, the blade faces a gauntlet of tests. It's bent, twisted, and pulled, sometimes to the point of near breaking. Hydraulic rams simulate hurricane-force winds, flexing the blade through millions of cycles to mimic decades of operation. Sensors capture every micro-movement, feeding data into supercomputers that predict how the blade will behave in real-world conditions. Only after passing this ordeal is the blade deemed ready for the outside world. But the journey is far from over. Transporting a blade the length of a football field is a logistical marvel in itself. Custom-built trucks inch their way along highways, accompanied by police escorts and teams of spotters. Traffic lights are lifted out of the way, roads are temporarily closed. Every turn, every bridge, every intersection is a challenge. Finally, the blade arrives at its destination, a wind farm, often in some of the world's most remote and windswept locations. Giant cranes hoist the blade hundreds of feet into the air, where crews bolt it to the hub with painstaking precision. When the last fastener is tightened and the last inspection complete, the turbine is ready to spin. But even here, the story isn't over. As the blade slices through the air, it faces a relentless barrage of forces, gusts, turbulence, even impacts from hail or birds. Inside, sensors continuously monitor its condition, transmitting data to control centers miles away. If a problem is detected, technicians can analyze it remotely, sometimes even activating tiny heaters or pumps built into the blade to prevent ice buildup or reduce vibration. All of this, every layer of fiberglass, every drop of resin, every micron of paint, serves a single purpose: to capture the invisible power of the wind and transform it into clean, renewable energy. The next time you see a wind turbine on the horizon, remember the incredible journey its blades have taken. From a handful of raw materials to a soaring feat of engineering, each blade is a testament to human ingenuity, a floating giant dancing with the wind and quietly helping to power the world. Is the extraordinary journey of a wind turbine blade, a story of ingenuity, precision, and the relentless pursuit of harnessing nature's power for a cleaner future.
Let's step back and imagine for a moment the raw beginnings. Each of these blades starts as nothing more than rolls of fabric and stacks of balsa wood. The fabric, glass or carbon fiber, is lightweight but incredibly strong, while the balsa wood, surprisingly, is chosen for its unique combination of stiffness and low density. Layer by layer, skilled technicians and automated systems arrange these materials into a mold the size of a passenger jet's wing. It's a process that demands patience and an almost artistic eye, as every layer must be perfectly placed for the blade to withstand the stresses it will face high above the ground.
But the magic truly happens during the vacuum infusion. Picture a gargantuan sandwich sealed up tight, as powerful pumps suck every bit of air from the mold. Into this vacuum, liquid resin is drawn, seeping through the fibers and wood, binding everything together. There's no room for error. If the resin doesn't reach every corner, or if air pockets form, the blade's structural integrity could be fatally compromised. The stakes are high. A single flaw, and months of work, and hundreds of thousands of dollars are lost. This moment is tense, with engineers monitoring every pressure gauge and flow meter, ensuring the resin's journey is flawless. Once the resin has thoroughly saturated the materials, the entire assembly is sealed and transferred to the curing oven. This oven is not a simple kitchen appliance. It's a chamber longer than a city bus, designed to heat the blade uniformly. Inside, the blade bakes at carefully controlled temperatures, activating the resin's chemical reaction. Timing is everything. Too little heat, and the resin stays soft. Too much, and it becomes brittle. Just a 15-minute deviation can spell disaster, warping the blade or leaving it too weak to fly. This stage is as much science as it is art, blending chemistry with industrial engineering. And then comes the moment of truth, the demolding. After curing, the blade is gently coaxed out of its mold. This is no easy feat when you're dealing with a structure that can weigh more than a dozen elephants and stretch longer than a basketball court. Specialized cranes, guided by laser alignment systems, lift and rotate the blade with millimeter precision. Any bending or twisting could introduce tiny cracks, invisible to the eye but catastrophic in the field. The choreography is slow, deliberate, and exacting, a ballet of steel and sensors. With the blade free from its mold, the focus shifts to refinement. Even the most precise molds can leave minor imperfections, so robotic arms equipped with sanding heads glide over the surface, sculpting it to aerodynamic perfection. Specialists, sometimes called blade doctors, work by hand to patch any tiny voids or blemishes, ensuring air will flow smoothly across the blade's surface. The inspection phase is rigorous. Technicians don clean suits and wield ultrasound wands and laser scanners, peering deep into the composite to detect flaws no human eye could spot. A single void, smaller than a coin, could eventually spell failure in the field, so every inch is scrutinized. Next, the blade is armored for the wild. Specialized coatings are applied, each designed to fend off a different challenge. Some layers protect against the relentless salt spray and moisture of the open ocean. Others shield against the sun's ultraviolet rays, which can degrade materials over decades. A particularly ingenious layer guards against lightning strikes. When a storm rolls in, Wind turbines are often the tallest objects for miles, making them prime targets for nature's fury. Embedded in the blade's skin are conductive strips, channeling the bolt safely down to the ground, sparing the delicate composite beneath. Before the blade can leave the factory, there's one final ordeal, the stress test. In a controlled environment, massive hydraulic actuators bend the blade, flexing it to extremes it should never face in real-world conditions. Engineers monitor every creak and groan, ensuring the blade rebounds to its perfect shape, undamaged. This trial by fire proves the blade's mettle, guaranteeing it can withstand the violent winds and ice storms it will face atop a turbine tower. What's truly remarkable is the custom nature of each blade. There are no generic, off-the-shelf solutions in this industry. Every site brings its own unique challenges. In the thin air of high-altitude plains, blades must be optimized for lower air density. In the salty, gusty conditions offshore, they're armored for corrosion and stress. Even the local wildlife plays a role in the design. Some blades feature serrated trailing edges, inspired by owls' wings, to reduce noise and minimize disruption to nearby birds. Sensors embedded in the blades can even track performance and health, sending data back to operators for years after installation. From start to finish, the making of a wind turbine blade is a blend of human craftsmanship, cutting-edge technology, and scientific rigor. It's a process that demands precision at every step, from the careful layering of fibers to the final punishing stress tests. And it all serves a higher purpose, capturing the invisible energy coursing through our skies and transforming it into clean, renewable power for homes, businesses, and entire cities. So, the next time you see those elegant giants spinning on a distant ridge or rising from the ocean's surface, remember the story behind each blade. Behind their silent grace is a world of innovation, teamwork, and relentless attention to detail, a testament to what we can achieve when we blend imagination with engineering. This is the art and science of wind power, where every revolution marks another step toward a more sustainable world.